Well, hello. Welcome back. So we're on chapter 4 now. Chemical bonds. Here are our learning objectives. Okay, so start out by talking about carbon. Carbon is a very strange element. I personally have done research with carbon. I've done it in vacuum chambers. What's weird about carbon is it forms straight chains, and this is really important for life. So if you look at some science fiction, people talk about silicon-based life form rather than carbon-based life form, and I can tell you it's very, very different. I've also done research on silicon. When you throw silicon to atoms together, they form kind of clusters. After like about 19 atoms are left less, they kind of form sort of these football prolate structures, and greater than 19 atoms, they form these kind of spherical, start as cage-like, and then it turns into spheres. Uh, so carbon, if it wasn't for carbon, we wouldn't have life as we know it right now, because so many structures require long chains, things like cell membranes, DNA, proteins. Proteins can be blobs, but things like hair, and that's a protein called keratin that you need to have long chains. Anyways, here I am babbling on. Carbon Carbon's very versatile, and it is held together by chemical bonds. So we'll talk about other things as we go on. So why do things bond? Why do things actually bond to form chemical bonds? And the answer is because it's lower energy. So we talked a little bit about this before. That electrons are like people. Electrons and atoms are like people. They like to be in low energy. So if you're going to be doing something for a long time, you want to do something that's low energy. In fact, I'm lying down right now as I'm making this video. And the noble gas configuration, so that's the last column of the periodic table, those number of electrons, that's 2, 8, 18, and so on, those are relatively low energy levels. So uh, I'm sorry, 2, 10, 18, excuse me, 2, 10, 18, I was saying 8 with a octet roll. Those are relatively low energy configurations. So I also mentioned the octet roll. The 8 is the 8 number of valence electrons. And so there's a couple ways you can do it. So you look at sodium, has 11 electrons. It needs to get to 8. It has 1 valence. It can either gain 7 or lose 1. What's it going to do? It's going to lose 1. It's lazy. It's too hard to gain 7 electrons. Besides, 7 electrons one thing, those 7 electrons, they're all negatively charged. They don't like each other, and they repel each other. So, and sodium is just doesn't have a strong enough, has a positive enough nucleus to keep 7 extra charges around it. So it ends up just losing an electron instead. And chlorine has 17 electrons, and it can gain 1 to have the same electronic configuration of argon with 18 electrons. Again, these numbers, they're low energy. That's the reason why we're doing this, because this is low energy. And this was first proposed by Lewis. And Lewis, this is a funny, interesting thing. Lewis thought that electrons, or that atoms were like boxes, and electrons were like the corners of a box, and a box has 8 corners. And so when he drew this, he's like, oh, atoms are like boxes, and for some reason they like to have the number 8 around them. And he got the right answer, but for the wrong reason, kind of thing. Like you ever done that? You take a class and you get the right answer, and the teacher marks it, gives you half credit, but you got the right answer. Like, well, you did it the wrong way. I got the right answer. You argue back and forth. That's what happened with Lewis. You had the right answer for the wrong reason. And here's an abbreviated periodic table showing that, and this is the groups. So hydrogen in the alkalis there with 1 valence, alkaline earths group 2A with 2 electrons, and so on. Boron family with 3, carbon family of 4, nitrogen family with 5, oxygen family of 6, halogens with 7, and noble gases with 8, with say of helium just has 2. And things bond to be like noble gases because that's lower energy. And we know sodium does in fact react with chlorine. It's a very explosive reaction. And we get salt, table salt, sodium chloride. And how does this work? Well, sodium transfers one electron, one of its electrons, it's specifically its outermost electron, to the chlorine atom, and then it becomes the chloride anion. And then why does this react? Well, it's held together by the lattice energy. So if you look here, that the picture on the bottom left marked A, you have the larger green chloride anions and the smaller purple sodium positive ions. And if you see that the way that they're joined together, this is a simple lattice as well as a simple cubic lattice. There's different types of lattices. Depends on what it is. Like diamond, for instance, has a different structure. So, and the idea is that the plus and minus ions are really close together, but then you have the pluses and the pluses and the minuses also close together. But you see they're kind of diagonal to each other, so they're further. They repel. The like charges repel, the unlike charges attract, and that combination between the attraction and repulsion is what keeps salt the way it is. It has that, or any sort of ionic compound that way. It's a combination of those, and you can. It's pretty simple to do. You just use the Pythagorean theorem and look at the charges and use Coulomb's law. That's it's the charge of one times the charge of second over the distance squared times the constant 1/4 pi epsilon naught. That's Coulomb's law, and we could spend the whole class doing this and calculating out lattice energies, but that's kind of boring. Besides the fact there's a shortcut you can learn in later classes if you follow more chemistry. Although I think most of you probably aren't going to be chemists if you're taking this class. I'm just saying that because this is a class for non-majors. If you're wondering, you use something called the Madelung constant, and that's a geometric thing. Anyway, so table salt there, and another thing. This is a nice illustration for ionic compounds. Ionic compounds tend to be brittle. So if you look at the picture still marked A, if you hit it with a hammer and you move the chloride ions down by one, you're gonna by one atom, and now you have the negative ions next to negative ions, and the structure doesn't like that. So then the salt crystal will just break. That's why salt's so brittle. I mean, you can take a hammer and pound salt and it'd be dust. It's really easy to do. So ionic compounds tend to be brittle. But then you look at metals, the metallic bond is different. Metals tend to be more ductile or bendy. So metals are very different than crystal lattices. So anyways, next slide. And atoms and ions, very different. Atoms are neutral, ions are charged. So octet rule, I told you this before, they tend to gain or lose electrons, so they have 8 valence electrons. And that's from the S and the P's. So there's 2 s electrons and 6 p electrons. So 2 plus 6 is 8. And that's also why hydrogen and helium only bond to get to 2. Well, helium tends not to bond. It can, but it tends not to. So at least not in this scope of this class. Metals. So metals lose ions. Lose electrons, become cations, and nonmetals gain electrons to form anions. So remember, the T is the +1, so metals are +1, this one's the metal. So the T is the plus sign, cations are positive, anions are negative. Okay, so here are some common ones. So hydrogen and the halogens tend to have +1, alkaline earths tend to be +2, and so on. So they don't mention carbon here. Carbon can be plus or -4. It tends to be minus more than it's plus, since 4 is ionic compounds. So okay, and going on. So when we're in the middle part, so looking at copper now, the middle part of the periodic table, the transition metals, those are different. The rules governing them are a little harder, and you can learn about this in future classes. So the charge, so how do we name things? So it's pretty easy. Some of them have simple, like alkalis and alkaline earths, there's only one charge. So alkalis only have +1 and alkaline earths only +2. And you can see here that in 1B, 2B, and 8B, there's, zinc is only 1, but copper can be 1 or 2, iron can be 2 or 3. So how do we name this? We'll start with the simple ones here. And the anion, how do you name the anion? It's the base root of the word plus IDE. So chlorine uses the base root chlor and then IDE, so chloride. Oxygen is ox plus the IDE oxide. So now when you name two simple ions that has a metal that only has one charge and then a non-metal, so NaCl, it's sodium, the name of the metal, chloride. So sodium and chlorine, sodium chloride. Magnesium and oxygen, so it's just going to be right, you say magnesium or right magnesium and then oxide, magnesium oxide. And now when there's more than one charge, so if you have iron plus 2, iron plus 3, you would write iron and then 2 in Roman numerals. So Roman numerals, I is 1, II is 2, III is 3, IV is 4, V is 5, and VI is 6. So and when you say it, you say like for iron 2, you say iron 2, whatever, chloride, oxide, that kind of thing. Okay, and here are the trends with the periodic table, and this is why the periodic table is written as such. It's the electronic properties of the atoms. And you see here the alkali is going to be +1, alkaline earths +2, and then going towards the noble gases, the other rest of them, nitrogen tends to gain 3, oxygen tends to gain 2, halogens tend to gain 1. And then you have various other ions in other places in the periodic table. You don't have to memorize the middle part. That's kind of silly. And for this class, most of this stuff will be provided to you or be accessible to you. So don't sit around and try to memorize this stuff. So covalent bonds. So we talked about ionic bonds. Ionic bonds involve sharing or transferring of electrons. Covalent bonds deal with sharing of electrons. So, and it depends on the number of electrons shared. So 2 electrons shared, you have a single bond. 4 electrons, a double bond. 6 is a triple bond. And, but anyways, we're talking about naming still. So you use the prefix to figure out the number of elements. And for the first element, we drop the word mono. But for the subsequent elements, you have to include mono. There's only one. But those are the prefixes to the number of the atoms in each element. And I didn't mention, we also have some common names too, like H2O, water. We don't call it dihydrogen monoxide, we just call it water. NH3, we don't call it trihydrogen nitride, we call it ammonia. And hydrogen peroxide, we don't call it dihydrogen peroxide or dihydrogen dioxide. Peroxide deals with the negative on oxidation state on the oxygen. So those are all proper names for it. But if by this convention you don't call it dihydrogen dioxide, you call it hydrogen peroxide. Anyways, so how do you name it? You have the prefix plus the name of the first element. Except for the first, if the first element is only one, we drop the word mono. And the second name, prefix plus the root name of the second element plus IDE. So let's give an example. So sulfur and 4 bromines, we use the full element's name sulfur, and then the word 4 tetra, and then bromine bromide. So sulfur tetrabromide. And 2 phosphorus, 3 oxygens. So it's not one. You have to use for the first one. You have to include the number word. So diphosphorus for 2, trioxide for 3 oxygen. So diphosphorus trioxide. Okay. And again, we are changing topics, what we do quite frequently in the beginning of this class. Electronegativity. So this is the ability for an atom to attract electrons to itself. Like, have you ever gone to an event and you see like go somewhere like I don't know, Halloween and in Lahaina or something like that, or Honolulu Halloween. I mean, sometimes there's just a really attractive person, and almost a ring of people form around that really attractive person, and people like to look at this person. So that is kind of like electrons. Electrons are attracted to certain types of atoms, and the most attractive atom to electrons is fluorine. And the reason why is fluorine is a tiny atom, so you haven't learned about periodic trends. As you move from left to right across the periodic table, the atoms decrease in size. So fluorine is a really tiny atom with a +7 center. So that -1 electron is really attracted to this really tiny +7 nucleus. I know it's 9, but the 2 electrons shielded, so it's effectively a +7. And if you look at potassium over there, the K and the pink end in the far left, potassium is a very big atom, and it has a +1 center. So you have this +1 charge that's a very large atom versus a +7 charge that's a very tiny atom. Electrons can get closer to the +7 charge, and they're more attracted to the +7 charge. So that's why fluorine. It has to deal with size and charge. So if you look, oxygen is also a very electronegative atom. It's the second most. Fluorine is the most. Oxygen is the second most. So the ability of atoms to attract, the atom's ability to attract electrons is important. And this is because if you have different atoms. So what do you do if you have two different atoms? So hydrogen and chlorine. So hydrogen and chlorine can form a covalent bond. They share electrons, and they can bond as such. So and problem is chlorine is more electronegative, is more attractive. So because of that, the electrons are drawn towards the chloride, the chlorine nucleus, and so the chloride end of the molecule has a slightly negative charge. So what do I mean by slightly? I mean less than -1.6 times 10 to the -19 coulombs. That's a charge of an electron. And likewise, hydrogen is a slightly, that delta, that's lower, that kind of funny looking D thing, that's lowercase delta in the Greek alphabet. And it usually means partial. So that means partial in science and math. That partial +1 charge, it means partial because it's less than +1.6 times 10 to the -19 coulombs. So, and you have a partial charge there. Another way to think about this is a blanket hog. Like if you've ever shared a bed with someone and you're under covers with that person, maybe you or the other person is just a total blanket hog. It gets cold, and then how do you respond to the cold? Well, you wrap yourself with the blankets, like in like a little burrito, and then the bed mate, who is not covered in blankets, is really chilly. It's really cold, yet the other person is full of blankets and feeling really warm. That's kind of what's going on here. You have hydrogen and chlorine. Chlorine is the blanket hog, stealing the blankets, stealing the electrons away from hydrogen, and then hydrogen is kind of left kind of chilly. Like it doesn't have a full charge there. It has a little less electrons. And something to note about electrons, I know you can see the picture, hydrogen and chlorine there. You have the dots. You have the dot structure, the Lewis dot structure. Electrons are kind of like this fuzzy gas that's in many different places at once. So I say electron density. Electrons can be in more in one place at the same time. They're really tiny. This is part of the field of quantum mechanics. And it's like, well, where are the electrons? Is it spend a little bit of time in hydrogen and a little more time in chlorine? It really spends, the electron is both around the hydrogen and it's around the chlorine at the same time, but it has more of its density around chlorine. So again, this is quantum mechanics. It's a really fascinating and confusing field. So the electron density is that way. So it's kind of fun if you want to read up on this. These are fun things to study. I remember I started learning this a lot in depth with quantum mechanics right when Harry Potter came out in the books, and I would read Harry Potter and study quantum mechanics. And I mean, it was like, oh, like both magic. It was like it helped me. It made me feel a little better about quantum mechanics, because it makes no sense in a classical sense, the classical mechanics sense. But I could kind of feel like I was at Hogwarts, and I was at Berkeley. Berkeley was my Hogwarts, I guess you could say. All right, but polar covalent bonds, this is unequal sharing. So we have covalent bonding. If you have the same atom, they share equally. If you have two different atoms, you have unequal sharing. And then this bond polarity, we show that there. That's the polarity means it's not even. And So this slide here, I do not agree with this slide. So my own personal opinion, I do not agree with this, and it doesn't really matter for this class. Part of it is I'm a physical chemist, and so I study the physics of chemistry of sorts. Um, this slide is to make organic chemists happy because in organic chemistry you consider the hydrogen-carbon bond to be completely covalent, but it's not. It's really polar. Easiest way to remember is if they're the two of the same atoms, it's covalent. If it's two different atoms, it's um, non-polar covalent. I'm sorry, polar. I'm sorry, polar covalent. If it's two different atoms, polar. If it's the same, it's non-polar. And if it's a metal and a non-metal, it's going to be ionic. So now that I said that, I'm going to tell you an exception to the rule. Polyatomic ion. So polyatomic. Poly means many. So if you are in a polyamorous relationship, that means, so poly means many. Polyamorous, many loves. You have more than one. If you're a monogamous relationship, mono means one. So monatomic ions are one atom. Polyatomic ions are many atoms. And so it's two or more. As you can see, you have hydroxide and cyanide at 2, and then you have various others that are much higher. And these many atom ions, here's some common ones. Again, don't have to memorize any of these. The idea is many atoms form an ion, and then that charge is associated around that molecule. And here's some more for you. Okay, so formulas for these, you have to put if it's more than one, you have to put parentheses to denote it. So if there's only one, you can just leave the polyatomic ion written as is. But for calcium nitrate, calcium is +2, nitrate is -1. So the two nitrates need to balance out the calcium +2 charge. Parentheses are put around the nitrate ion, and the subscript indicates the number. So when you see NO3, that subscript on the bottom of the oxygen, that means that NO3 means there's 3 oxygens, and if there's nothing given, it means 1. So 1 nitrogen and 3 oxygens for nitrate, and then the parentheses there for 2, that means there's 2 of those units. So calcium nitrate has 1 calcium atom, 2 nitrogens, and 6 oxygens. So and I'm getting the numbers by taking 2 times those numbers there. So nitrogen not listed as 1, so two nitrate groups means 2 nitrogens, and each nitrate has 3 oxygens, so 3 times 2 is 6, if you're wondering how I'm getting those numbers. Okay, and you put them in simply order, and the positive ion goes first, if you're wondering where you get the name. So ammonium is NH4 plus. It's a positive ion, and the charge for the ion, you can see it's in the top right superscript. There's always the charge of the ion. Okay, and much of this is beyond this class for sketching Lewis structures. If anything, you would only have to do the really simple ones. But let me go over the rules anyways, in case you do take future classes that do this. So how do you sketch Lewis structures? First one is you sum up the valence electrons, then you put the skeletal structure. How do you put the skeletal structure? You put the biggest atom or the least electronegative atom in the center, and then you put the other ones around it. And then put electrons on the outer atoms to get octets or duets for hydrogen. And then you have to, whatever's left, you put around the central atom, and then add double and triple bonds to complete an octet. That's how you do a Lewis structure. And here are some samples. So hydrogen, so you can see the Lewis symbol there is just the hydrogen dot is just one hydrogen with one dot, and hydrogen tends to form one bond, and it can form single bonds with hydrogen and other. I mean, it's formed single bonds with all elements. You don't have to know this, but I'm trying to entice you to study more science. Hydrogen can form other types of bonds. It can form something called a bridge bond. It tends to do that with boron quite frequently. There's some ions like H3 plus, so 3 hydrogens can form a molecule, a plus molecule. And helium here, so tends not to bond. You can get helium to bond. It's hard to get to bond. It'll form molecules in the sun. So the sun has something called dihelium, He2 plus. So you can get helium to bond, but it's for this class though you don't. It's inert. It doesn't react. But the truth of the matter is you can get helium to react. It's difficult to do it. So carbon, the most interesting element, at least as far as a life sciences is concerned, tends to form 4 bonds. Nitrogen and phosphorus tend to form 3. Oxygen and sulfur tend to form 2. Fluorine and the other halogens tend to form 1. Okay. And there are some exceptions to the octet rule. One of them is an odd number of electrons. These are known as free radicals. So some nitrogen oxides, for instance, are free radicals. And this has various applications. So free radicals are used to start plastics. So when plastics are formed, you have a free radical starts the reaction. Free radicals are very important for fires. So for a fire to continue, you need 4 things. It's known as a fire tetrahedron. You need fuel, you need an oxidizer, you need heat, and you need the chain reaction. The chain reaction is free radicals. If you remove any of those, the fire goes out. And there are fire extinguisher techniques called halons. Halons put out fires, and how do halons work? Halons release halogens, which are free radicals under heat, and then those free radical hydrogens are electron scavengers, as they know. They get rid of free radicals, and then the fire goes out. We also, part of our stealth technology, the molecule SF6, sulfur hexafluoride, is added to jet fuel, and that, in the heat of the jet engine, has a fluorine radical, I should say. Fluorine radical is an electron scavenger, and it makes the fuel burn very cleanly, and you can't track the soot trail on radar. So those are some applications for free radicals. If you're a nutrition person, the vitamin C is an antioxidant. There's several other antioxidants. Vitamin A is an antioxidant. Vitamin E is an antioxidant. And what the antioxidants do essentially is they get rid of free radicals. And how does vitamin C work? Well, pretend like you imagine there's 10 hungry teenagers coming in, and you have these Brussels sprouts that you want to make sure the teenagers don't eat. Like, how do you prevent a group of hungry teenagers from eating some Brussels sprouts? Well, what you do is you put a bunch of Halloween candy in front of the Brussels sprouts. And what the teenagers do is they come and eat all the Halloween candy, and then they're not hungry and they won't eat the Brussels sprouts. Right? So how do you prevent your DNA of your cell from being destroyed by random high-energy free radical molecules? Well, you put vitamin C in your cell, and the free radical will go for the vitamin C and leave your DNA alone. So same idea. So that's free radicals. Very, very reactive, and we have antioxidants to protect us. And we also use that to put out fires, to start some chemical reactions like polymers, and we also use it as part of our stealth technology. So, fun stuff. Okay, now let's talk about molecular shapes. And sometimes we call it VESPR, but it's VSEPR, valence shell electron pair repulsion. So this is a theory. It's an incorrect theory, but we still use it because it works really well. It has some problems that it's predicted some incorrect chemical properties of molecules, specifically, most notably the magnetic properties of oxygen. But this was an amazing theory that makes lots of sense. That is too bad it's not true, because it really makes so much sense. So the idea with VSEPR is that molecules form shape. And this is true. This part of the theory is true, based off of the repulsion of negative groups. So if there are two groups, the atoms will align themselves such that they are linear, and they're as far. The idea is that they're as far away from each other as possible. If there are three groups, they will form 120 degrees from each other. That's 2 pi divided by 3 for those radian folks. Likewise, linear is 180 degrees or pi radians. And then the idea is a circle divided by 3 for 3 sets, and this is known as a trigonal plane, or sometimes trigonal, trigonal, however you want to say it. Both are fine. And then for 4 things, this is tetrahedral. So linear and trigonal planar, you can model this in a 2-dimensional plane. Tetrahedron has 3 dimensions, so that's why it's going to skew there. So atoms can go into 3 dimensions. So while linear is 1-dimensional of sorts, planar means 2, so 2 dimensions. But linear you can draw on a piece of paper. Tetrahedral though, need to have it. It's a 3D thing. Okay, so here is the VSEPR chart. And if you have, again, this is a bit above and beyond the class, but I am talking about it so you can read about it. And learn in future classes, if you will. But let's look at this. So for the number of bonded groups there, we have two bonded groups that forms linear. So for 3 bonded groups, so and all 3 are for 3 electron groups and all bonded, then that's going to be planar. And if you I'm going to go to the bottom. I don't like this chart. For 3 bonded groups, 2 bonding, 1 lone pair. This is known as a bent structure. Let me go to the middle again to 4. So 4 groups, all bonding. This is tetrahedral. Next one down, 4 groups, 3 bonding, 1 lone pair electrons. This is going to be pyramidal. So specifically trigonal. So triangular pyramidal. Then for 4 things, 2 bonding, 2 lone pairs, this is a bent structure. And why is this important? Because of molecules being polar and nonpolar. So molecules that are polar, meaning that there's a charge to it. The charge, of course, is, so one end of the molecule is charged. One is positive, one is negative. Like we talked about hydrogen chloride. So hydrogen chloride is a polar molecule. And unfortunately, I hate to regret to tell you that this slide is wrong. That in order for a molecule to be polar, 2 conditions must be that it must have polar bonds. This is incorrect. Actually, you can have a molecule that does not have polar bonds. So whoever wrote this, I'm sorry, but you missed this in your editing process. So this is mostly true. Most molecules have to have polar bonds. Ozone, 3 oxygens, that's a polar molecule, and it doesn't have. It's doesn't really have. It's by this book's definition of polar bonds. It's the same atom. There's no electronegativity difference. So then you would say it's a nonpolar covalent. It's a fuzzy question. But rule number 1 here is wrong, but it's usually right, except for a very few cases. But I guess I do have a PhD in chemistry. I can be eccentric. And then the bonds must be arranged such as the separation charge. Well, the separation charge, that defines what polar means. So, duh. So you have to have a separation of charges. And this is important because polar molecules have different properties. There's something called the like dissolves like rule. Polar molecules like to be around polar molecules, and nonpolar molecules, well, they prefer polar molecules, but they can only really hang out with nonpolar molecules because the polar molecules won't let them. Those bastards. Okay, so if you look here, so methane here, so carbon tetrahydride, so we call it methane though. There's 4 things, although this is saying it's a polar bond. Wow, you're saying it's a polar bond. That disagrees with the previous slide that I said was wrong. All right, but the idea is that the electron density is flowing towards the carbon, but since you do not have a side of the molecule that's positive or negative. This is a nonpolar molecule. And here with ammonia, though, that you have electron density going towards the nitrogen. So because of that, you have a partial negative charge in front of the nitrogen, and then you have a positive charge that's around the hydrogen ions, or well, not ions, hydrogen atoms down there. So this is, ammonia is a polar molecule, and here's water. Water has electron density going towards the oxygen, so you have a negative end of the molecule and then positives around the hydrogen. One of the easiest ways to remember, all bent and all pyramids are polar. All so linear, trigonal, planar, and tetrahedral. If all the atoms are the same, it's going to be nonpolar. If one atom is different, it's going to be polar. So that's and also all hydrocarbons are nonpolar. Those are kind of easy rules to remember, and again, this is kind of above and beyond this class, but you get the joy of listening to me lecture as part of this. So okay, green chemistry. Teaching quite a bit about sustainability here and learning about these things about bonding. We can develop new things, and we can either improve it to lower energy. So lowering energy costs is a big thing. Reducing wastes. We do this now in the pharmaceutical industry. We look at medicines, and we do computer simulations on them to prevent uh, to have less testing. So an example of this are acid reducers. So there's the proton pump inhibitor Prilosec, and Prilosec has as a combination of drugs, and they studied it and they isolated one of them partially due to looking at the bonding, and they formed a new drug called Nexium. So Nexium is just an isolated form a drug from Prilosec. We do this quite extensively with HIV research, so antivirals. It's antiviral drugs. We don't have as many as we do, like, say, antibiotics, and this is an emerging field, and we have to rely heavily on bonding and looking at the life cycle of the virus and figuring out what part of the life cycle of the virus we're going to attack to provide drugs for destroying that virus. And so that's the green chemistry, and as we're doing this, it's with the understanding we're doing less laboratory work, and laboratory work is expensive and it's hard on the environment because it uses a lot of resources. Chemistry in the lab is not a cheap science, if you will. It requires lots of space, lots of energy to keep the space pristine and clean, use lots of water use, and you produce some gnarly toxic waste. And so less the amount of time that you spend in the laboratory as far as a green chemistry standpoint, the better. Okay, and so some we're wrapping up this chapter here. So we have some names here. Ammonia, of course, ammonia is a common name. Chemical formula, nitrogen and 3 hydrogens. So if you look at that NH3, the nitrogen, there's no subscript. This implies 1 nitrogen and then 3 hydrogen atoms. And then the Lewis structure, looking at this, you have nitrogen with single bonded 3 hydrogens. A hydrogen wants to have 2 electrons, so that line indicates 2 electrons. So each hydrogen is happy because 2 electrons. The nitrogen has 3 of those single lines and then 2 electrons to itself. So 3 of the lines, 3 times 2, that's 6 electrons that it's sharing with hydrogen, then 2 on its own, that's 6 plus 2, 8. The nitrogen has 8 electrons. It obeys the octet rule. And then looking at the VSEPR, with having the 4 groups, 3 bonding, 1 lone pair, that is the trigonal planar geometry as denoted there by that molecular model. So that's what we talked about in this class. And there's the end. Okay. Thank you, and see you next time.